Hello and welcome. Introduction. In this video, I would like to compare and contrast assembly language and a high-level language like C. I will refer to the programs from my last two videos as examples in my discussion. Now, in my previous videos, I use assembly language and C to control an LED using the TM4C 123GH6PM microcontroller ADC module. I have provided the links to those videos in the description. The programs. So what I'm going to do here is this. I'm going to display both the programs, that is the C program and the assembly language program, side by side so that we can see the difference. So here on this side is the C version of the program, and on this side is the assembly language version of the program. So what I'm going to do is I'm going to scroll down, and this is where the C program ends, but the assembly language version carries on. So we scroll down, and we scroll down again, and the assembly language ends here. Now, so the first obvious difference is the length of the program. As you can see, the C program is much shorter. The assembly language and C program performs identical tasks. That is, to turn on an LED using the TM4C 123GH6PM microcontroller ADC module. However, the programs, I'm referring to the programs, differ in terms of syntax, abstractions, and readability. Now, I'm going to compare and contrast the assembly language and the C language using the programs shown earlier as examples. Compare and contrast. Abstraction layer. Now, assembly code operates at a low level, meaning it directly interacts with hardware registers and memory addresses. Now, each instruction corresponds to a very specific machine level operation. What that means is, for example, loading a value into a register or storing a value in memory. Now, for example, let's take a look at LDR R0, equals ADC0 underscore PSSI. Now, what this means here is loads the address of ADC0 underscore PSSI register into register R0. Now, ADC0 underscore PSSI has been assigned a hex address at the start of the program. Okay, so here is the starting of the program. I showed that earlier. So here is ADC underscore PSSI, and it's equate and is given a hex address, which is 400388028 hexa. So it has been assigned this address. Let's go back. So what that means is that address is being loaded or copied into register R0. Now, a C program operates at a higher level of abstraction. What I mean by is that is using variables like this ADC result, all right, and uses functions and a structure control flow. If you look at this part is highlighted in green. So we have a while loop here, another while loop, and then we have an if-else structure. So it uses a structure control flow. So the hardware interactions are extracted using symbolic names like ADC0, arrow PSSI, instead of using 4003828 hexa. All right, so it uses this instead of this. And here is an example. We have an ADC0 underscore arrow operator PSSI bitwise all operation with this 08 hexa value. And the programmer doesn't need to know the exact memory address. Readability and maintainability. Now, for assembly code, the assembly program is harder to read and understand due to its low-level nature. Now, it requires a detailed knowledge of the hardware architecture, for example, the register addresses, as we've seen in the earlier example with the ADC0 underscore PSSI. It was assigned a hex address. That's what I mean by register address. And then there's the bit manipulation. Here is an example. LDR register R1, comma, equals hexa 08, and STR register R1, comma, square brackets R0. Now, these are what I meant by hardware architecture. All right, the register addresses and so on. Now, these instructions are not that intuitive. Without understanding the hardware context. Now, if we look at the C program, it's more readable and easier to maintain. It uses meaningful variable names, as we've seen earlier. For example, ADC result was one of the variable in the C program, and then the structured programming constructs like if statements and so on. So here is an example that I extracted from the program. If brackets ADC0 result greater or equal to 048. Now this is more intuitive than using assembly code like this, CMP R2, comma, hash 2048, and then BGE LED on. So this is more intuitive when compared to these instructions. Portability. Now, the assembly program is highly specific to the target hardware. For example, the ARM Cortex-M4 processor used in this video. Now, porting the program to a different architecture, for example, the x86, would require rewriting the entire program. Now, the C program is more portable, as it can be compiled for a different architecture with minimal changes. Example, the same C code could be compiled for an ARM or x86 processor with appropriate compiler support. Development time. Now, writing and debugging assembly code is time-consuming due to its complexity and low-level nature. It also requires careful management of registers, memory, and hardware-specific details. Now, for C code, development time is generally shorter, less error prone due to the high level abstractions and built-in language features. For example, in our two programs that I've shown earlier, functions like enable clocks and initialize ADC0 function encapsulate complex operation, making the code easier to write and debug. Let's take a look at an example. Now, I've extracted this two portion of code from the programs that I've shown earlier. So this is the C initialize ADC0 function. All right, so this is the C initialize ADC0 function. And this is the equivalent in assembly language, the initialize ADC0 proc function written in assembly code. Now, you will notice the high level of abstraction in the C function. All right, it uses symbolic names like ADC0, ACTSS, and so on to configure the ADC registers, which abstracts away, taking away the low-level details of the memory addresses and direct register manipulation. Now, in contrast, the assembly code is more complex. All right, it involves in loading the memory addresses into registers, performing bitwise operation, and then storing the result into registers. Now, each step in the assembly code corresponds directly to the hardware operations, which requires deeper understanding of the processor architecture and instruction set. Memory usage. Now, assembly code uses less memory as it does not include extra libraries or stack management. Now, each instruction corresponds to a specific machine instruction, making it memory efficient. Whereas the C code uses more memory due to function calls, stack frames, and runtime libraries. Some additional memory is allocated for local variables. Let's take a look at a couple of examples. Okay, so I'm in my Keil Microvision IDE, and I have put up the code, the assembly version of the code here. Now, I'm not going to go through the code, but what I like to do is go to Project, and then rebuild all targets. It's assembling it. And then let me just zoom in here. I'd like you to take a note of the code size or the program size. Let me just draw the program size or the code size. In this case is 556 bytes. Okay, so this is the Keil Microvision IDE again, and this time I've put up the C version of the program. All right, as before, I'm not going to go through the program. What I like to do, as before, go to Project and rebuild all targets file. Right, and I like you to take note of the code size again. But this time for the C, the code size if I just put a box around it, the code size is 964, 964 bytes. Okay, so as we have observed earlier, the assembler language code or program takes up 556 bytes of memory, 556 bytes, whereas the C code takes up 954 bytes of memory, 954 bytes of memory. The question is, why is that? Let's take a closer look. Okay, so this is the Cal Microvision IDE. I have put up the assembly program up here. There's one thing I like to point out before I go any further. I have named this file adcasm.s. Now, if I just zoom in just to have a quick look, so it's adcasm.s. Now, you can call this any other name, right? I chose to call it adcasm. And the extension is a .s file, signaling that this is an assembly program. Now, this .s file is actually a pure text file. You can use Microsoft Word to open it. It will read it, or a notepad. So what I've done is I have opened it up using Notepad, and it's here, the same text file that you've seen earlier. This is just purely to demonstrate that, to show that the .s file is just a text file. Now, we need now to translate this into machine code, or assemble it, or compile it. Now, to do that, in Cal Microvision IDE, we go to Project, and you got two options. Either you use a build target or rebuild all target files. Now, I'm choosing to use rebuild, and we got 0 error, 0 warning. And let me just download it to the board. Go to download. All right. So it's download, program done, everything okay. Yeah. Now, before I go any further, let me just put a breakpoint here. And then I go up to debug. And then start debug. And then let me just run it. So it stopped here at the breakpoint that I set earlier. Now, the reason for doing that, I just want to highlight this instruction as an example. Now, this instruction, if you see, is also up here in the disassembly version. The build process has turned this .s file into its machine code. Now, this is not the machine code. This is this one here with the hex values. This is 00003AC. This hex value here, this is the address of the location. Now, in that location, you have another bunch of hex values. In this case, it's 482A. 482A. This is hexa. This is the contents of this location. This 482A is the machine code of this. And it is this machine code that gets executed. All right. Now, as you can see, the machine code is pretty straightforward in the sense that there are no extra baggages around. So, for example, what I mean is LDR, this instruction is being translated to this, and then the next instruction is translate into this, and so on. All right. So this is the assembly version of the, or rather the assembled version of this program here. Let's move over to look at the C version of this. Okay, so we are looking at the C program, or the C version of the program. So I'm going to go to project, all right, and then I'm going to do a rebuild all target files, and I got 0 errors, 0 warning. Let me download it to the board, and it says programming done, verified, okay. So if I go to debug, start the debug. Now, if you're wondering why I want to go to the debug session, it's because in debug session, I can see the disassembly version. All right. So let me just scroll down to the, and then let me highlight this instruction here, ADC, arrow, operator, PSSI. So if I click that, and you see the disassemble version here, notice for this one line of instruction or statement, it generates this amount of machine code. Only for this one here, this amount of machine code. Now, if I choose the while part, this, and which is this one here, look at the amount of machine code produced. All right, it's a fair bit of what we call amount of machine code for a straightforward statement like this. And let's take another one before we move on. This ADC result here, and it's here. And again, you find that for a one line of statement, you get this amount of machine code. And as you can see, that's why the C program takes up more memory. Is assembly language still relevant? I would say yes, assembly language is still relevant, and most modern development or software development is done in high-level languages. Now, assembly still plays an important role in specific areas where performance, efficiency, and low-level hardware control are critical. Now, I want to focus on one particular area, that is the embedded systems and microcontrollers. Now, microcontrollers have limited resources, such as the RAM, ROM, and processing power. Now, writing certain parts of the firmware in assembly can improve performance and reduce memory usage. Now, understanding assembly language is valuable for tasks like embedded systems development. Programs are usually written in a high-level language, but critical parts like ISRs, that is interrupt service routines, startup code, and performance-sensitive functions may be written in assembly language. Now, for real-time system, bootloaders, or firmware development, assembly still remains relevant. Conclusions. Okay, so let's take a look at the this table. Basically, I have summarized all that I have discussed in this video in this table. So let's look at, first of all, look at readability. All right, for assembly language, it could be difficult, but for C, it's well, it is a lot easier because of its structured nature. Then the code size, As you can see, the assembly language is smaller, the code size, and the C language, because it incurs overheads, the code size tend to be larger than the assembly version. Execution speed for assembly language is faster, it's more optimized, whereas in C, it's slightly slower and it's compiler dependent. Portability for assembly language is not so portable because it's architect specific. For example, if you're using ARM, then you are stuck with ARM. And if you want to change it to a x86, then you have to rewrite the entire program. Whereas C is more portable, but it's compiler dependent. Then the development time for assembly language is a little bit slower because it's manual and tend to be error prone. Whereas C language, as you've seen, is shorter. For debugging, generally speaking, assembly language debugging an assembler program is harder than compared to the C language, where it's easier. And then the final point I'd like to make is memory usage. It is lower, more efficient, and but that is for the assembly language. And for C, the memory usage is higher because of the extra overhead. Okay, that's it for this video. I hope you have found the contents useful. I thank you for watching, and I'll see you in the next video. Bye!